This lesson deals with a Class D amplifier. You can find these notes in the ECE402 ebook in Chapter 9, starting on page 1. Several years ago, ECE402 was what was called a capstone class. This is a class that had a group project, and we had teams of up to 5 students working on a particular design. This is one of the projects that we did. But before I go into some of the details of that, let me explain why we're doing a Class D amplifier. In the 303 lab, we built a Class B amplifier, and we showed that its maximum efficiency was 78.5%. But this is when the output was maximum, and that the efficiency dropped off as the signal got smaller. And we'd taken measurements to show that in lab. Here's a graph of showing the efficiency versus the ratio of the effective output versus the maximum output. So here's a ratio of 1. As you can see here, as the signal gets smaller and smaller, the efficiency drops off. When we're reproducing music, only about 1 or 2% of the time do we actually need maximum power out to pick up those peaks in the music. So for battery-operated systems, a Class B amplifier isn't really very efficient. In this capstone project, we started with an article that was in Popular Electronics in 1996 on how to build a switching amplifier. Many companies now sell modules that do this, but I wanted the students to see how the internal workings of this amplifier worked. And let me just pull up the article right here. It's describing this 60-watt amplifier. And on the second page, it shows the schematic. On the bottom of the page is feeding a signal into here, and this is creating 51 volts, 12 volts, minus 12 volts, and minus 51 volts. And then over here is a triangle wave oscillator, and that's being fed into a comparator circuit that's going to compare music to a triangle wave. We'll talk some more about that in a little bit. This is a 2-channel output. So here's one channel, here's the other one. So here's the right out, and here's the left out. And so this comes into a signal conditioning circuit that hooks up to a series of transistors that creates a switching output. So this is my power amplifier, and likewise a similar one for the left channel. On the bottom of the page is a schematic of creating the larger voltages of the plus and minus 51 volts. We'll talk some more about this a little bit later in the next lecture. Let's go back into the notes. Let me start out my explanation of the Class D amplifier with the comparator portion of the circuit. What's feeding it is the triangle wave, and the triangle wave is oscillating at a frequency that's higher than our largest frequency of interest. In this case, we're going to be looking at an audio signal from 20 hertz to 20 kilohertz. And the frequency of this oscillator is somewhere around 40 to 50 kilohertz. So let's take a comparator. Let's hook up a signal here. That's just a triangle wave. And then feed our audio signal here. What's going to happen? Well, when the audio signal is bigger than the triangle wave, the output will go high. And when the triangle wave is bigger than the audio signal, the output will go low. I better show you this with a little bit of a simulation. Here's my triangle wave. It's at a much higher frequency than my audio signal. I just picked a point out here. Here, the audio signal is bigger than the triangle wave for this little instant in time, and so the output of the comparator is going to go high. Over here, the opposite's true. The audio signal is smaller than the triangle wave, so the output's low. So you can see here, when the audio signal is bigger, we have a waveform that has a duty cycle that's closer to 100%. And over here, we have a duty cycle very close to 0%. Now, as you approach the center of that sine wave, we get what looks to be a square wave. Let me summarize this. And so the duty cycle is greater than a half when the audio signal is positive. The duty cycle is equal to about a half when the audio signal is 0. And the duty cycle is less than a half when the audio signal is negative. Let's next take a look at the output stage. Here we have 2 MOSFETs, an N-channel and a P-channel MOSFET. And our power supply is actually going to be plus and minus 24 volts. The article actually had a mistake in it. We'll talk some more about that in the next lecture. The signal conditioning circuit that's hooked up to here is going to be producing a pulse that's either 16 volts or 24 volts on this line, and minus 24 and minus 16 on this line. So when this is 16, this will be 24. When this is 24, this will be minus 16. Now these MOSFETs have a very low on resistance. This particular one had about 300 milliohms, and this one about 160 milliohms. What happens when the signal here is equal to 16 volts, and this is equal to minus 24? Well, if it's equal to minus 24, then the voltage across the gate source is 0. And these MOSFETs have a threshold around 4 volts. So this would be cut off. The source to gate voltage here, from here to here, would be equal to 24 minus 16, so it'd be 8. And that would be greater than threshold, and that's enough to put it into the ohmic region. So this becomes a low resistance. So what happens with the load? Our output voltage here is going to be the 24 volts voltage divided with this resistance. It's basically be our speaker. And the resistance that's here. So it'll be the load over the load plus the on resistance. But because this is a couple hundred milliohms and this is going to be on the order of 8 ohms, this is roughly equal to 1. So you get about 24 volts out. Now what happens in the opposite case? Well, if this is 24 volts here, then the difference is going to be 0. And here, the gate source would be minus 16 minus a minus 24. So we get a plus 8 again. So this is greater than threshold. And now this one is going to be in ohmic. This one's going to be in cutoff. And again, we got a voltage divider. So the voltage here, minus 24, times the load impedance divided by the load plus the resistance here, which is about 160 milliohms. And then again is a voltage divider very close to 1. So our output voltage in this case is equal to minus 24 volts. What this power amplifier is doing is actually amplifying the pulse. What's going to be coming in is a much smaller voltage that's conditioned by a BJT circuit. And then we're going to use these MOSFETs to basically increase the voltage. So now we've had our pulses and we're going to make them larger. So we've taken our music and converted it into a series of pulses. This is called pulse width modulation. So we're converting the audio signal into a series of high frequency pulses. Now we're going to filter out the components to give us our audio signal back. So if you had a low pass filter here that had a corner frequency less than the frequency of our pulses, then we're going to be passing just the average value of this circuit. At a 50% duty cycle, then the average value here would just be equal to 0. And that corresponds to when our music was 0. Now if we had a duty cycle that was close to 100% or greater than 50%, so now this is going to be giving us a DC value, low frequency value, of about 24 volts. And so when the audio signal was maximum, we're going to get the maximum of our positive power supply. And if we had a low duty cycle, say close to 0% or less than 50%, the average value here is roughly minus 24. And our low pass filter is going to pass low frequencies compared to the frequency of our pulses. And so we would pass the minus 24 volt component. So we're going to piece together our audio signal. What we've been able to do is actually make it larger. Let's design the low pass filter. Now in the article by Bourbon, he suggested using the speaker itself as a low-pass filter. Well, when we actually built our first capstone project, we found out that it didn't work well. In fact, it sounded horrible. Most Class D amplifier manufacturers suggest putting a low-pass LC filter. So we're getting out a signal here that's swinging between the power supplies, and I'm going to deliver as much power as I can to the load. So putting it through an LC filter will consume very little power in the and design a fourth order filter. 20 N dB per decade would give us a roll-off of minus 20 times 4, or minus 80 dB per decade, or minus 24 dB per octave. Well, we actually looked at some of this in Chapter 3. And so we're going to design a low-pass Butterworth circuit. We'll set the corner frequency of this at 20 kilohertz. Our triangle frequency is going to be between 40 and 50 kilohertz. That's going to be 1 or 2 octaves higher. So we want to roll it off as steep as we possibly can. We could add more components, but actually N equals 4 works pretty good. We're going to assume that the speaker is equal to 8 ohms. Now the resistance looking back into our MOSFETs is a pretty low resistance. And our load is basically 8 ohms as an approximation. So we have the case where our source resistance is much, much smaller than our load resistance. Let's go back to pages 23 and 24 of our Chapter 3 class notes. And this was the case where we had the pi and the T network. The T networks were the case where this was much smaller than the load. So we're going to take the case of N equals 4. That will be on the next page. And we're going to grab these components to make our filter. So let's go back to the Chapter 9 notes. So grabbing those values off of 1.5307 henries for L1, 1.5772 farads for C2, 1.0824 henries for L3, and 0.3827 farads for C4. Well, again, those are very large values of L and C, but we're going to scale those. Make our corner frequency 20 kilohertz, R sub L of 8 ohms. We're going to use our scale factor of M, which would just be the value of our resistor, scaling it from this case of a 1 ohm resistor to an 8 ohm resistor. Multiply 2 pi by 20 and get 125.66 kiloradians per second. We're going to take a magnitude and frequency scale. So our value of L1 is going to be M times bigger, which is 8, and then smaller by 2 pi F naught. For C2, we're going to divide by M, divide by omega naught. So divide by 8, divide by 2 pi F naught. For the L, we're going to again multiply by M, divide by omega naught. And then for C4, we're going to divide by M and divide by omega naught. That's going to give us 97.4 microhenries. The nearest standard one is 100. 1.569 microfarads. The nearest is 2.2 microfarads. 68.9 microhenries. 68 is the nearest. 0.381 microfarads. 0.33 microfarads is the nearest one. So now we can use that filter to transfer power from the power MOSFETs to the load without losing a lot of it in between. Now, all of the ICs and the transistors that are used in this design are also in the ECE402 library, which again you can find on my homepage, and you can use that for the simulation of this circuit. In this design, we're going to use some electrolytic capacitors, and I got some low ESR capacitors for the project. Because we had seen some problems with stability in our voltage regulators, I thought maybe we'd start out with something which has a minimal effect and we have more an ideal capacitor. Now, the model for a capacitor is a capacitance, a series resistance, but there's also some lead inductance. This capacitance is very large, and the resonant frequency of this L and C can be quite low. In our particular case, it was around 13 kilohertz. Again, that's in the audio band. When the frequency is very low, this dominates the series combination. You basically just see the capacitance. As you increase frequency, the magnitude of this impedance begins to decrease, and you begin to see the effect of the ESR. You get to this point, these two are resonating, and all you see is the effective series resistance. Now, once you pass this resonant frequency point, the impedance of the inductor is now greater than the impedance of the capacitor and begins to look inductive. So obviously you don't want to operate too much over here because now our capacitor is really an inductor. In some designs you'll see that they'll actually put a capacitor in parallel with a large electrolytic capacitor, and the idea is to have some higher frequency filtering to get rid of this effect. Now, because this was a capstone project, I was suggesting how they should measure these things. I suggested that they measured the effective impedance of this, which would be dominating by the capacitance at around 100 Hertz with our LCR meter in the 402 lab. And then to measure the effective resistance when we are maybe closer to 1 kilohertz. This is going to get a little bit smaller compared to this. And then lastly, to measure the inductance at the highest frequency of the instrument, which is about 1 megahertz on the LCR meter. And so you're able to get some numbers on a model for their simulations. The other capacitors in this design are less than a microfarad, and so I decided to use polyester film capacitors. These are the ones we typically use in the 402 lab, and these are very glossy encapsulations that are typically green or orange or red or yellow. They have self-resonant frequencies that are greater than a megahertz, and so that's beyond the capability of our LCR meter, but also way beyond the frequency we're looking at with our triangle wave and our audio signal. So our model would just be a series resistance and a capacitance. Unfortunately, the series resistance is very frequency dependent. So if we take a measurement of it, it should be at a frequency that we're seeing our biggest effects, and that would be the frequency of our triangle wave oscillator, which is somewhere around 50 kilohertz. So I recommended that the students measure the C sub S and the R sub S, which would be our equivalent R and C here, at that frequency. The same was true for the inductor. Its self-resonant frequency is beyond the megahertz, and so I'll have a measure of the effective series resistance and inductance at the frequency of the triangle wave. We're going to do this so we get the most accurate simulation around 50 kilohertz, and we'll see this pulsing into our waveform, causing a little bit of distortion. This was a capstone project. We broke this into different pieces, and so we had one person on the team designing the switching amplifier. I had that person use the 200 watt power supplies we have in lab. The other members of the team are going to use the switch mode power supplies we did in the previous chapter to design the plus and minus supplies for this overall system. Because we're using a lab power supply, I have to be mindful of the fact that it does have a voltage regulator inside of it, and you can run into problems because of that, because the regulator will not let current go into the power supply. And sometimes during switching, those things happen. Decided to model the power supplies here with just a battery and then a diode so that current could come out of here, but current can't go back in again. So if there was a switching transient with this power amplifier, that it can't pump current back in here, because that won't happen in lab. Now, because we're adding a diode here, in fact, the power diode, we should add 1 volt to the voltage here so that we get the voltage here we want of the 24 volts. Now, we're also using different size wires in our design. We have some banana wires and we have hookup wire. So I give a model for the banana wire, which was about 6.4 milliohms per foot and about 94 nanohenries per foot. And then for the hookup wire that we were using, about 26 milliohms per foot and 94 nanohenries per foot. Sometimes this inductance can cause effects or stability problems, and so it'd be good if our model was accurate, even down to the wires that we're going to hook up. In our next video, we'll take a look at a piece-by simulation of this circuit, and then take a look at some of the problems with implementing the power supply that was in the magazine article. And this is a Class D amplifier.